Hi guys, welcome back here at DC Engineering Tutorial. So this time is we're going to talk about the water movement in soil. Okay, so what we have here is a layer of soil, and then we have these crops. No? Okay, so bali ito yung crops natin. So yan yung land surface natin. So ito yung tinatawag natin na root zone soil water. Okay? And ito yung tinatawag natin na intermediate water. So, yung line between the root root zone soil water and intermediate water, we call it belt line. And this one is the capillary fringe rise. And we have this groundwater table, and we have this capillary fringe rise. Fringe water rather. Okay. And we have this impermeable layer, and we have this groundwater table or the petriatic water. And then we have internal water. And this is the bottom line. Okay? So, ito yung mga different layers ng soil natin in terms of soil water. Okay, so bali, kung makikita natin itong soil water, no, kung saan yung root zone natin, yung intermediate water tsaka yung capillary fringe water, that is part of the zone of aeration or the unsaturated soil zone, or we call it BADUS zone. No? While itong phreatic water or the groundwater, this is part of zone of saturation. Okay? Or we call it phreatic zone, or we call it tension saturated zone. And ito namang internal water, this is under zone of rock flowage. Okay? We have this unsaturated soil zone or the zone of aeration. Then we have this tension saturated zone or the zone of saturation and zone of rock flowage. Okay, so itong soil water, intermediate water, capillary fringe right, we also call this one, itong tatlo, as vadose water, okay, or the suspended water. And okay, and ito lahat, we call it interstitial water. Okay, ito lahat. Okay, so ayan. So makikita natin yung infiltration during rainfall. So yung water from rain is seep through our soil, no? So we call it infiltration. And after that, we call it deep percolation. Okay. And then we have this capillary action, no? Or the capillary rise. And we have this groundwater recharge. Okay. So dito naman sa crops banda, so at this layer, okay, so we have this root extraction, no, using yung tinatawag nating osmosis sa biology. Okay, so provided ito yung roots natin, no? So we have this root extraction na pumapasok sa mga ugat natin, no? Through stomata. And yan, we have this capillary rise. So ito yung tinatawag natin na evaporation, yung tubig sa lupa, no? Yung land surrounding the crops natin. We have that evaporation, and yung tubig naman na andito sa plants, we call it transpiration, no? Or combination ng dalawa, no? We call it evapotranspiration. Okay? Okay, so So, ito yung water movement in soil. Let's say, let's go back.
Smallest. Water moves more quickly through the large open macropores found in sandy soils than the smaller pores of silt or the much smaller flat-shaped micropores in dense clay soils. Soil structure also impacts water movement.
For a while.
Smallest. Water moves more quickly through the large open macropores found in sandy soils than the smaller pores of silt or the much smaller flat-shaped micropores in dense clay soils. Soil structure also impacts water movement. Water moves more quickly downward in soils with granular structure than a soil with platy structure that forces a longer indirect path downward. Other structures include prismatic and subangular blocking. Water is nearly always moving in the soil, and it can be in any direction simultaneously. Gravity is the dominant force that moves water downward. Restricted soil layers of compacted soil or bedrock are among the reasons water moves laterally. Capillary action, the attraction of water into soil pores, can move water in any direction. Gravity is the primary water-moving force in saturated soils, while capillary actions are the primary forces in unsaturated soils. Capillary force is greatest in soils with small pores. Water moves more slowly through these soils. Small.
So, yun, no? So, we have also this water flow in unsaturated soil. So, Darcy law for velocity of flow in the saturated soil applies also to unsaturated soils. So, however, as moisture content decreases, cross-sectional area through which flow occurs also decreases, causing permeability to decrease. So, we have also this intake characteristic of soil. So, intake rate is the rate of entry of water into underfilled conditions. So, this varies with many factors, including the depth of water, the surface, the temperature of water and soil, the soil structure and texture, and moisture content of the soil. And it varies from place to place on a field and time. So the best method for measuring intake is to obtain a direct measurement by recording the water applied less the water flowing from the field. When direct measurements are not feasible, intake cylinder can be used with reasonable success. So the cylinder should be at least 9-inch in diameter, made of smooth top steel, strong enough to dry but thin enough to enter the soil with a minimum of disturbance. So yung length natin is 12-inch long, and 5 tests should be made in a given location. Infiltration is another important property of soil which affects the surface irrigation. So it not only controls the amount of water entering the soil, but also the overland flow. Okay. Infiltration is a complex process which depends on the soil properties, the initial moisture content, the previous wetting history, the permeability and its changes due to surface water movement, the cultivation practices, the type of crop being sown, and the climatic effects. So in an initial dry soil, the infiltration rate is high at the beginning of the rain or irrigation, but rapidly decreases with time until a fairly steady state infiltration is reached. So this constant rate of infiltration is also termed the basic infiltration rate and is approximately equal to the permeability of the saturated soil. So if we take our x-axis as our infiltration time in hours and the y-axis as infiltration rate I in centimeter per hour, so ito yung makuha nating curve, no? Ayan, di ba? So it decreases yung infiltration rate over time, no? While yung cumulative naman, no? Pero yung amount nung na-stored na water is increasing, di ba? During rainfall. So that is our cumulative infiltration Z in centimeter. Okay, so infiltration and soil water during irrigation. So let's say we take our x-axis as the water content and let's say our y-axis as the soil depth. So we have this initial water content and we have the saturated water content. No? So at this zone, we call it saturated zone. Then below that, we call it transition zone. And after that one, we have this constant transition, which is the transmission zone. And then we have this medyo turbulent na nga part, which is our waiting zone. No? So, yan yung layer ng ano. So, bali dito sa saturated zone, extending up to about 1.5 centimeter below the surface and having a saturated water content. The transition zone, which is about 5 centimeter thick and is located below the saturated zone. So in this zone, a rapid decrease in water content occurs, and the transmission zone in which the water content continues slowly with depth as well as the time, and the waiting zone in which the sharp decrease in water content is observed. No? So makikita mo man dito, no? Pa-decrease yung water content until such time na almost slowly na, no? Like almost linear na siya, and then ito, no? Decrease in water content, sharp decrease in water content sa waiting zone. So the waiting front is a region of very steep moisture gradient. So this represents the limit of the moisture penetration into the soil. So we have these three distinct zones. Nakikita natin doon, we have this transmission zone, which is the moisture content is essentially constant regardless of the direction of flow. The waiting zone is the moisture content reduces rapidly as waiting front is approached. In other words, dry soil with low permeability result in a greater loss of energy per unit length. And we have this waiting front, which is in the effect of capillary fringe, the foremost part of which has an average moisture content equal to the original soil. So we have this basic infiltration rate, depending on yung soil texture niya. We have the sand, sandy loam, clay loam, siltil clay, and clay. No? So we have also mga respective porosity niya, field capacity, and the permanent wilting point. So we have also soil that are non-homogeneous and also anisotropic, meaning that the permeability not only varies from point to point, but that value of the permeability in one direction is different from the value in other direction, even at a given point within the soil. So the limitation of the equation varies, but the value applied to those equations are not precise. No? This is to develop more practical method of measuring the soil properties over extensive areas rather than more precise determination at a point in the soil. Okay, so I think that's it, no, for water movement of soil. Thank you.